Hello, today we will be covering Chapter 3, Acid and Base Chemistry. First we'll start by defining the Bronsted-Lowry terms for acid and bases. So this is going to be a dynamic pair that we have, and a lot of the reactions we'll use in organic chemistry will involve acid-base chemistry. An acid, or a proton donor, is going to be a molecule that has the ability to donate a hydrogen proton, whereas a base is going to be an atom or molecule that has a proton acceptor, which is generally going to be a lone pair. So the way we want to kind of think about this is the hydrogen is going to be an empty shell. The proton is an empty shell. The s orbitals on the proton are going to allow it to form a new bond with a lone pair from a different atom. Here we have a hydrogen-chlorine bond. The chlorine, very electronegative, right? It's sharing these two electrons with the hydrogen, but most of the electrons are being hogged by the chlorine here, which makes the proton, or the acidic proton, have the ability to form a new bond with a lone pair on a different molecule. So that's going to be our acid, the molecule that has a proton attached to an electronegative atom, such as chlorine or oxygen or nitrogen. And our base is going to be a lone pair on an electronegative atom that can form a new bond with the proton. So the proton can basically be shuttled around between two different lone pairs. You can see on the right side of the equilibrium arrow, the chlorine now has both of the electrons that were in this original hydrogen-chlorine bond, and we've used one lone pair of electrons here to form a new bond with the proton. So we have the conjugate base of the conjugate base of the acid. So the conjugate acid results when a conjugate base accepts a proton, and a conjugate base results when an acid gives up a proton. So the conjugate base of the acid is the deprotonated form, where the two electrons from the bond are now on the base, and the conjugate acid of the base is going to be the protonated form of that base. So we have two sets of pairs here. Well, I guess really three sets of pairs here. We have an acid-base pair. The acid is donating a proton to the base. These two are reacting together. The lone pair electrons move in, attack the proton, and form a new bond, and the hydrogen-chlorine bond is broken. And we have a relationship between the acid and the conjugate base, right? The conjugate base is the deprotonated acid. And then we have a relationship between the base and the conjugate acid. The conjugate acid is the protonated base. So if we look at this reaction down here, we can first try to identify the acid and the base. So this molecule has a lone pair with a negative charge. This molecule has a proton attached to an electronegative atom. So this is going to be our base, and the water molecule is going to be our acid in this case. Once the equilibrium occurs, we're going to have the conjugate acid, the protonated form of the base, and we'll have the conjugate base, the deprotonated form of the acid. This event is called a proton transfer. The proton is being transferred from one molecule to the other molecule, or a protonation event. We looked at curved arrows in Chapter 2, and we used them to signify bonds being broken and bonds being formed. So we're going to employ our curved arrows in the acid and base reactions. Here we have B. This is representing a base. Remember, electrons are flowing from negative to positive, In this case, the positive is represented by proton, an empty s orbital. Most of the electrons in this bond between the acid and the proton are being pulled towards the acid, an electronegative atom. So we can show the electrons from the base forming a new bond with the proton, and we can see the bonds from the proton and the acid, the electrons from the bond and the proton and the acid breaking and moving towards the acid. So this is going to be two curved arrows to represent a bond being formed and a bond being broken. Here's another example. We have hydroxide anion. This is a base. And then we have acetic acid as our acid. We're using a lone pair on the hydroxide anion to deprotonate the carboxylic acid. This first arrow is showing a new bond being formed, and the second arrow is showing a bond being broken. This forms water as our conjugate acid, and the acetate anion as our conjugate base. So here's a reaction that's going to show several different arrows. We have a multi-step reaction here. And we can go through each of these arrows one at a time and answer the question, which steps here are proton transfer steps? So our first arrow, we have a lone pair. The electrons are forming a new bond with the proton. That would be a proton transfer, right? We have a bond being broken between the hydrogen and the oxygen. So the proton is being transferred from this oxygen to this oxygen. So this first step, proton transfer step. In the second step, we have a carbon-oxygen bond breaking. You can see the electrons from this carbon-oxygen bond are moving towards the oxygen. We have water leaving as a leaving group, and so that forms a carbocation. Now this step would not be a proton transfer step. Notice the protons are not moved at all in these arrows. All right, we have two more arrows here. We have a lone pair on oxygen forming a new bond with the proton, and the electrons from the carbon-hydrogen bond here forming a pi bond with the p orbital of this carbon that the carbocation resides on. So this is also a proton transfer step because this proton is being transferred from the carbon to the oxygen. So hydrogen has three different forms that we're going to learn about throughout the semester. And today we're really focusing on this first form, proton. So hydrogen has an s orbital. It can hold up to 2 electrons. A proton is a hydrogen that has 0 electrons in its s orbital, right? It is a positively charged proton, positively charged hydrogen. The hydrogen atom exists when we have 1 electron in the orbital, and hydride is going to exist when we have hydrogen with a negative charge and 2 electrons in its orbital. So this proton transfer event is going to be quantifiable. So we can actually determine between an acid and a base what percentage of the molecules are in the form of the conjugate acid or in the form of the conjugate base. And the way that we can determine this is through a dissociation constant. So that's going to be the pKa, and that's how strong or weak a base is. What percentage in water of the acid is going to be protonated and what percentage is going to be deprotonated. So in this equation, we have water on the left and the acid. And then on the right side, we have the deprotonated acid and protonated water. And that constant is going to be a ratio between the right side of the equation divided by the left side of the equation. Or what percentage of it is going to be a ratio between the protonated water and the protonated acid. This equilibrium will give a percentage of the molecules found on each side of the arrow. And this will be relative to the concentration of each molecule in the equation. We can use this KEQ to determine the strength of an acid when it's dissolved in water. So overall, the concentration of water isn't going to change that much, so we can actually remove that term from the equation. And as the strength of the acid, or the amount of water that it can protonate, increases, then the association constant Ka will also increase. So if we have a strong acid, then we're going to have a very high Ka, and if we have a weak acid, then it'll be a number smaller than 1. Because we have such a large range of Ka values, of association constant values, we're actually going to use the pKa to work with the strength of acids. So this is going to be a negative log value of the association constant. If we use this negative log value, it'll give us a range of values from -10, or a very strong acid, to 50. A lower pKa is going to be a stronger acid. A higher Ka value is going to be a stronger acid. This means a larger amount of the water molecules will be protonated than attached to the acid. In general, for this course, we're going to be mostly working with pKa values, or the negative log of the Ka values. Here is a pKa chart, and we can start here in the top left. We have sulfuric acid, and this is showing the protonated form of the acid. This has a pKa value of -9. This is the conjugate base. -9 is extremely acidic. On the opposite end, we have an alcohol, ethanol, tert-butyl alcohol. These are around 16 to 18, and water is around 15.7. Generally, water is a good baseline to compare the acidity of molecules to. This value here at -1.74 is the hydronium ion. So any acid that has a pKa lower than this is going to be considered a strong acid. So in water, these acids will completely protonate the water. So for example, if you have HCl, you're going to have complete hydronium ion and no HCl. It's all going to be converted to the hydronium ion if we mix HCl with water. So as we move up to the top here, we can see our strongest acids, and as we look on the right side here, the conjugate bases of the acids, as we go to the bottom, we have the strongest bases. So if you're comparing the acidity of two different molecules, we can use the pKa table to compare them. If you were to compare the acidity of two molecules, whichever molecule has a lower pKa is going to be more acidic. Or if we were going to compare how basic two molecules were, we would then look at the conjugate base, and whichever molecule had a conjugate base with a higher pKa, it would be more basic. Each of these pKa units represents a full order of magnitude. So if we were to compare these two different ethanols, these two different alcohols, ethanol would have a pKa of 16. Tert-butyl alcohol has a pKa of 18. This is 2 orders of magnitude. So ethanol is 100 times more acidic than tert-butanol. You guys should memorize the pKa values for water, ethanol, phenol, and the hydronium ion, and as points of reference to compare the rest of the acidities to. The stronger an acid we have, the weaker its conjugate base. So we can also use this table to compare the strength of bases. A strong acid is going to be completely disassociated in solution, meaning that all of the protons will be attached to water. These two acids, you'll never find a sulfuric acid that is completely protonated in water, and you'll never find HCl that's protonated in water. All of the protons will go react with the water to form the hydronium ion. The same trend holds true with strong bases. Here we have ethane, ethylene. In solution, a strong base is going to be partially unassociated. So we have ethane, the conjugate anion of ethane is actually the strongest base. This negative charge is on the carbon, and we have a strong desire to form a new bond with a hydrogen, with a proton. So any proton around this is going to almost immediately react with it. Strong bases are going to be almost completely associated with proton in solution. So if you were to expose this ethane anion to any form of proton, it's going to immediately react and form ethane. Our pKa table and values allow us to predict the equilibrium for a reaction. So based on the pKa value, we can determine which of the acids wants to hold the proton more. Whichever one is weaker acid is going to be more likely to hold the proton. So here we have a relationship between tert-butanol and water. Those are the two acids that we're comparing, and we have a pKa difference of 2.3. Because the tert-butanol has a higher pKa, it's going to be a weaker acid, and it's going to be less likely to give up its proton. Water is going to be a stronger acid in this case, so it's going to be more likely to give up its proton. That means our equilibrium is going to lie in the direction where we have the tert-butanol protonated and the water deprotonated as its conjugate base. The equilibrium will always favor the weaker acid and the weaker base. A strong acid wants to give away its proton. In this case, water has the lower pKa, so it's the strongest acid, and it's going to give away its proton to form its conjugate base. The stronger base will always want to receive a proton. In this case, tert-butanol has the higher pKa, therefore it's going to have a stronger base and be more likely to receive the proton. In organic chemistry, we're going to utilize these large pKa differences to execute chemical reactions. So if a pKa difference, for example, is 34 units, that's 10 to the 34th more products and reactions. And this is no longer really an equilibrium arrow at this point. It's just a reaction arrow. It's not going to be a reversible process. So if we take a strong base and react it with water, then we're going to be able to fully protonate that base irreversibly. Sometimes we don't actually have a perfect value for the pKa. Those are experimentally determined, and there's a database that has most of the pKa values in it. But there are properties of the molecule that we can use to qualify the acidity without actually knowing the specific value. And so we're going to go through 4 different properties of the molecules that will affect their pKa. If we want to determine the relative strength of the two acids without knowing the specific value, we're going to compare the stability of their conjugate bases. So remember when we looked at the electronegativity of an atom like oxygen and chlorine, we said that those atoms were able to stabilize the negative charge or the extra electrons better because of their electronegativity. This is going to be a similar trend that we see when we're comparing acidity. We're going to look at the stability of the conjugate base. So once that proton has been removed, the electrons or the negative charge that are left over, how stable is that conjugate base? How stabilized are those electrons? Based on the stability of those electrons, we're going to have a stronger acid. So the stronger the acid, the more stable its conjugate base is going to be. So let's look at the stability of the lone pair. There's going to be 4 factors that we look at to determine the stability of the lone pair. The type of atom that carries the charge, or the electronegativity. We can also use resonance to stabilize a negative charge, which we talked about a bit last chapter. And then we'll talk about 2 other factors that are involved, which are induction and orbitals. So the first place we're going to start is by actually drawing out the conjugate base. Here we have 2 molecules, butane and propanol. If we wanted to compare the acidity of those 2 protons, then we have to determine what the conjugate base is going to be first. Sorry for the square boxes here. These should be negative charges. The conjugate base of butane is going to be deprotonated, and we have a lone pair with a negative charge. The conjugate base of propanol is shown below. It'll be oxygen with 3 lone pairs and a negative charge. So first, let's look at the electronegativity. The type of atom that carries the charge is going to play an effect as well. The larger the atom, the more stable the negative charge will be. Carbon and oxygen are relatively similar sizes. They're right next to each other. So we'll have electronegativity. The oxygen having 0.5 more electronegativity units is going to do a better job at stabilizing the negative charge that's built up when the molecules are deprotonated. Since the propanol is going to be more stable, the propanol anion is going to be more stable than the butane anion, then propanol is going to be more acidic than butane. And this is directly comparing the electronegativity of the oxygen compared to the electronegativity of the carbon. So for practice, you can compare some of these molecules. And when you're comparing the acidity for HF versus HCl, for example, we can use the comparison of the electronegativity of fluorine versus chlorine to help determine. We'll go through these problems on the worksheet. So the next factor that will affect our acid strength, or the stability of the conjugate base, is resonance. Here we're going to compare ethanol to acetic acid. First, we'll deprotonate both ethanol and acetic acid to generate their conjugate bases. So we have ethanol anion, and we have the acetate anion. Ethanol has the negative charge from the oxygen residing on 1 oxygen, stabilized by only 1 oxygen. Acetate anion has 2 resonance structures available. The first resonance structure stabilizes the negative charge on this oxygen, and then we can push the electrons up so that it's stabilized on this oxygen. Since this charge is delocalized across 2 atoms, it's going to be a more stable conjugate base, and therefore the acidity of acetic acid is going to be more acidic, meaning acetic acid is going to have a lower pKa than ethanol. And we can double check this by comparing the pKa of these 2 on the pKa table. The next factor which can be used to affect the stability of the conjugate base is induction. Electron withdrawing groups that are near the atom that builds a negative charge will withdraw electron density. So for example, here we have acetic acid, we have trichloroacetic acid. This bond between the carbon and the chlorine is going to have a dipole moment. Chlorine is more electronegative than carbon, so the chlorines are pulling electron density away from that carbon. And therefore, even though we're 1, 2, 3 bonds away from where the negative charge is going to build up on the conjugate base, those chlorines are still pulling that electron density towards them and helping to stabilize the negative charge. So, trichloroacetic acid is going to be more acidic than acetic acid. And we can look at a trend here. Acetic acid, pKa of 4.75. If we add one chlorine in, we have one chlorine to help stabilize the negative charge that gets built up on oxygen when a deprotonation occurs. That lowers the pKa or makes it more acidic by almost 2 units. And this is going to increase as we add more chlorines. So a second chlorine lowers it another 1.6 or so, and then a third chlorine lowers it all the way to 0.7. This is called the inductive effect. One additional factor to take into account is the type of atom. So the more electronegative the atom, the stronger effect. For example, if we had fluorine compared directly to chlorine here, it's going to be even more acidic because fluorine is more electronegative than chlorine. The final factor that we're going to look at, which affects the acidity of a molecule or the ability to stabilize a conjugate base, is going to be the type of orbital that is the negative charge is residing in. So the closer electrons are held to the nucleus, the more stable they're going to be. And if we look at the shape of the lobes, right, an sp orbital is going to have 50% s characteristic, 50% p characteristic, so it's going to be shaped more similar to an s orbital than a p orbital, whereas an sp3 orbital is going to look more like a p orbital than an s orbital since it's 75% p characteristic, 25% s characteristic. So if we compare these two protons and we draw out the conjugate base, we deprotonate them. The proton in red is going to lead to an anion in an sp2 orbital since it's attached to an alkene. The proton in blue is going to lead to a negative charge in an sp orbital. And we're going to have to ask which of these carbanions is more stable. The sp2 orbital is going to be less stable than when the negative charge is in an sp orbital. And that's because the sp orbital, remember, is smaller. Those electrons will be closer to the nucleus. So we'll have a more stable conjugate base, which means we'll have a more acidic proton when we're dealing with an sp orbital compared to an sp2 orbital. And the same relationship will hold true when we compare an sp2 orbital to an sp3 orbital. If we look at the pKa of these carbon-hydrogen bonds, right? These are actually some of the strongest bases here. Ethane, carbon-hydrogen bond itself is very strong. It's very stable. It's very difficult to break a simple carbon-hydrogen bond. We're going to have a pKa of 50. This is an sp3 carbon-hydrogen bond with a pKa of 50. If we look at an sp2 carbon-hydrogen bond, slightly more acidic. Those electrons that can be formed in the conjugate base are going to be held a little bit closer to the nucleus, but it's still relatively high pKa. And then finally, acetylene, getting closer to an acidic proton, but it's still a fairly high pKa, and that's with an sp orbital. So in summary, we have the electronegativity of the atom, the ability for the conjugate base of the atom to engage in resonance. We have inductive effects, and then we have the type of orbital where the charge resides as all being factors that are going to help us to analyze the relative acidity of different protons. These are all stabilizing effects that will help to stabilize a charge buildup on a deprotonation event. This order is not necessarily 100% reliable. There are going to be a few exceptions. So let's look at a couple of these exceptions. Ethanol is more acidic than propylene. Um, we can look at the two conjugate bases. We have ethanol. pKa is much, much lower than propylene. We have a consistency with the type of atom, oxygen versus carbon. But here we have the ability for the propylene to engage in resonance, right? We can push this lone pair to form a new bond here and then move the charge onto this carbon. So in this case, our order is accurate comparing the two factors, type of atom versus resonance, and the order that they come in. Let's look at this example. Here we have acetylene, pKa of 25, and we have ammonia, pKa of 38. We know, based on the pKa values, that the equilibrium is going to be in favor of ammonia. If we were to look at the order here, we would have concluded that the negative charge on a nitrogen atom, which is more electronegative than a carbon atom, will be more stable. However, this is not what the experimental values. So in general, for some acids, we need to look at the pKa chart and be able to determine based on the pKa chart. In this case, we have a little bit more complicated of an example because we have multiple factors that are in effect. So the pKa values from the chart will always be a higher priority than the ARIO kind of guidelines for determining acidity. So we can use these pKa values to predict the equilibrium position of a reaction. If you're given two acids and asked if these two acids are combined, what direction will the equilibrium follow? You should be able to do this using the pKa values. If you have the pKa value of one acid and the pKa value of a second acid, whichever pKa value is higher, then the equilibrium will lie in that direction. And then the other way to kind of determine that is to look at the relative stability of the bases. If you're not given the pKa value, right, then we can look at the bases and determine is one base more stable than the other base. And we have four factors now that we can look at to determine the relative stability of the bases. All right, let's take a look at a couple examples. So we have one carboxylic acid here on the left, and we have another carboxylic acid here on the right. Without the pKa values, if we wanted to figure out which direction the equilibrium lies, we would want to look, instead of the acids, we could look at the bases, the conjugate bases. So if we compare the conjugate base on the left to the conjugate base on the right, we see that the conjugate base on the left has a chlorine that through induction is stabilizing some of the negative charge that's built up on the oxygen relative to the right. So in this case, the direction of the equilibrium would be towards the left, favored towards the left, with a protonated version of this acid and the deprotonated version of the acid, the conjugate base of the acid with the chlorine. If we look at this next example, we have propanol versus the sulfur equivalent. In this case, we're going to have a comparison between the stability of these two conjugate bases. Oxygen is more electronegative than sulfur, but sulfur is going to have a far greater atom size than oxygen since it's below it on the periodic table. And then in this case, the equilibrium will lie to the left because we have a larger atom size on sulfur. When we start to do reactions, there will be a lot of places where we want to generate a negative charge and use a base or an acid to protonate or deprotonate a molecule. And so in order for us to do that, we need to make sure that we choose an acid or a base that's strong enough to deprotonate a molecule. So for example, let's look at acetylene here, the acetylene anion. So we can find that on the pKa table. If we wanted to generate this anion from acetylene, right, if we wanted to do this deprotonation, then we're going to need to use a base that's strong enough. So that would be any of the bases that fall lower on the pKa table than acetylene. To deprotonate this proton, we could use any of these three bases. These would all be strong enough. Well, let's look at the acetate anion. What base could we use to deprotonate this anion? If we find it on the pKa table, it's going to have a pKa of 4.75. So if we wanted to deprotonate acetic acid to form this anion, we could use any of the bases below it on the periodic table. All of these bases are stronger than the conjugate base of acetic acid, so all of these bases would be able to deprotonate acetic acid. So here are a few practice problems. We'll go through these when we go through the worksheet problems. So there are a few other factors that we want to take into account, the first of which is leveling effects. So acids that are stronger than the hydronium ion cannot be used in water. So if we have sulfuric acid and we dissolve it in water, this pKa is -9. This is one of the lowest pKa's. But actually, if we have sulfuric acid in water, dissolved in water, then the pKa is only going to be -1.7, and that's because all the sulfuric acid is going to be converted to the hydronium ion. And the same effect holds true with bases that are stronger than OH-. This is actually more important when it comes to bases because if we have water present, we're not going to be able to deprotonate something like an alkane because it'll just deprotonate the water instead. So the only time we can use water as a solvent is when the base is not stronger than hydroxide. We're going to have a variety of different solvents that we can use then. Bases are stronger than OH, cannot be used in water. We would have to use a solvent that's going to be aprotic. So here are 5 examples of aprotic solvents. These solvents don't contain any acidic protons. So this is tetrahydrofuran. There are no protons attached to electronegative atoms. And the same holds true for acetone, DMF, acetonitrile, and DMSO. So these are solvents that we can use in the presence of a strong base. Another effect that we can have with regards to solvents to take into account is the sterics. So if we look at tert-butanol and compare it to ethoxide, this is the electron density mapping of the molecule. You can see that in red we have our buildup of negative charge. Tert-butanol is much more sterically hindered. There's 3 bulky methyl groups compared to just 1 bulky methyl group hanging off. And so we'll have less solvent that can be used to stabilize the negative charge on the oxygen. And so this is why we see a 100-fold difference in pKa between tert-butanol and ethanol. If we mixed tert-butanol and ethanol together, then we would have almost all of the ethanol deprotonated and all of the tert-butanol protonated because the tert-butanol pKa is much higher, and that's because it's going to be more sterically hindered. Comparing ethanol to isopropanol to tert-butanol, ethanol is going to be the most acidic. Another impact on acidity is going to be the counterion in play. For the most part, these will be spectator ions. They're not going to necessarily be used to balance the equation, but they are impacting the overall charge of the solution. When we're writing out the reaction here, here's the overall equation. We have sodium, NH2, water, forming ammonia, sodium hydroxide. But we can actually get rid of sodium out of the equation as a spectator ion because it doesn't affect the equilibrium balance of this reaction. So we do not need to include all of the counterions when writing out some of these reactions. The final slide we'll look at is a Lewis acid-Lewis base definition. So we talked about Bronsted acid, proton, right, an empty shell, and Bronsted base being any lone pair that can react with the proton. A Lewis base is going to be very similar to the Bronsted base. It'll be any lone pair, but instead of reacting with the Bronsted acid, it can react with the Lewis acid. A Lewis acid is going to be any acceptor of electrons. So it doesn't necessarily have to be proton. That's the difference between a Lewis acid and a Bronsted acid. A Bronsted acid has to be proton. A Lewis acid can be other atoms. So for example, in this reaction on the bottom, we have a Lewis base, or a lone pair, reacting with the Lewis acid, and we have boron as the acceptor of the electrons instead of proton.